Hello everyone, my name is Fabian Kilger and I will be presenting our work on detecting and preventing faked mixed reality. This work is a joint collaboration between Alexandre Kabil and Marc-Oliver Pahl from IMT Atlantique, Volker Tippmann from the Fraunhofer Institute, as well as Gudrun Klinker and me from TU Munich. This work is also supported by the German-French Academy for the Industry of the Future through the Trivial project. As we can observe in the world, mixed reality applications are becoming more and more popular for work, leisure, and collaboration. Also, deepfakes are getting better and better already in the video and audio setting, and it is only a matter of time until it reaches mixed reality. Furthermore, mixed reality applications are often very distributed, and therefore the communication happens over many different types of networks and also the internet. Therefore, we must ask ourselves and carefully consider how secure are those mixed reality applications and what further measures can we take to secure them. But before we go into that, let's look at the dangers of faked mixed reality and why we even want to prevent it. And we can notice that already small deviations in the mixed reality can lead to big consequences. For example, let's look at the image on the right. There, we have a wall that is augmented with the pipes that are hiding beneath it. A construction worker wants to avoid these pipes as to not cause any damage or any leaks. However, if the augmentation is off just by a few centimeters, the construction worker will be deceived and might damage those pipes. Similar critical consequences we can observe for other use cases, such as industrial control systems, medical applications, such as surgeries, as well as management processes, where decisions could be made or influenced depending on faked mixed reality. In our work and in this presentation, we're going to show existing threats to the mixed reality pipelines and summarize existing protection techniques that can be used to mitigate those threats. Furthermore, we motivate and give ideas for a new detection mechanism for mixed reality on the client side. To first get an impression as to where an attacker can start, let's look at a management process that is supported by mixed reality. On the left in red, we see the normal management process, and in green on the right, how it is augmented with mixed reality. We can see we have many components as layers, such as the physical world, the managed system, management process, process data, and maybe even including a digital twin, visualization process, and finally the visualization hardware and the human at the top. Each of those components and layers can be attacked individually, but also the communication in between can be attacked. If data is modified at a lower layer, this will also affect the mixed reality and might lead to faked mixed reality. So what attack vector specifically can attacker use? And let's first discuss the network. A very common setting in network security is the man-in-the-middle setting. In this case, a malicious actor is in between the communication of two parties and can read what is being sent and possibly also modify, delete, or delay all messages. There are many scenarios how they can get to this position. A easy one would just be having a machine in between a cable connecting two machines or owning a specific router. And also in a local network, there are threats to that, specifically via ARP spoofing. ARP is the protocol used in the local network to map low-level MAC addresses to higher-level IP addresses. However, the ARP protocol doesn't have any protection for spoofing, and therefore an attacker can send malicious ARP packages and corrupt the mapping from MAC addresses to IP addresses for some machines in a local network. This ultimately can lead him to gain a man-in-the-middle position. Further care must also be taken for wireless networks. That is very easy for an attacker to interact with them or even to jam them. The VPA2 protocol, which is the one used for your phone and your notebook to communicate to a router. There has recently been an attack found, which is the crack attack, which in the best case allows an attacker to read data that is being sent on an encrypted channel, and in the worst case, even modify this data. Furthermore, VPA2 and even the newer version, VPA3, are vulnerable to dictionary attacks. This allows them to more easily brute force weak or mediocre passwords and gain access to the network, or even worse, leak an employee's credentials and impersonate them. Further care must also be taken for routing networks. Routing is, for example, used in the internet to find the fastest path from your machine to your destination. But it is also used in sensor networks to find the best path a sensor message should take to its destination. The problem with these routing protocols is that they often need some metric as to what nodes one other node can communicate with and how good or how fast they can do that. A malicious node can therefore advertise itself as being the best option or the fastest option to some nodes or even to all nodes. Therefore, the traffic will be sent to the malicious node and he would again be in a man-in-the-middle position. But there are also attack vectors lying higher up in the application level and further. Most notably, zero-day vulnerabilities. They allow an attacker often to infect a machine without any interaction and without even the owner noticing. For example, the WannaCry ransomware was able to attack and infect a lot of machines in a lot of time by abusing a zero-day vulnerability in the Windows operating system. Similarly, the Pegasus spyware was able to infect phones without any interaction and without anyone noticing by using a zero-day vulnerability in the iMessage app. Another and probably the most commonly used attack vector for in practice is social engineering. This, in a simple way, could mean phishing, where an employee is made to submit its credentials on a fake website, and therefore the attacker gets access to those credentials. It can impersonate the employee. Furthermore, it can give them access to more critical infrastructure that they then further attack. But it could also mean that an attacker is directly made to open a malicious file or even, in the worst case, to install malicious software. So what can we protect? How can we protect ourselves from those attacks? In communication, the go-to tool is usually cryptography, which can ensure the integrity and the confidentiality of our messages. Especially signature and certificate-based approaches like SSH and TLS are used over the internet to communicate with web pages, for example. And one can also think of using them for IoT, especially since the cost of IoT encryption is becoming cheaper. However, there are still some problems with that regarding performance and maintenance. Certificate schemes will also require a revocation scheme so that you can invalidate, compromise, and to all certificates. And this often incurs some maintenance overhead. Furthermore, cryptographic protocols require many messages to be sent to validate a certificate and also to exchange key material. And this increased performance overhead might be critical for real-time applications and mixed reality applications. Further protection in the network can be achieved through firewalls, which in simple terms allow one to separate different networks. And therefore, with the help of firewalls, one can protect machines from external traffic, so an attacker is not able to abuse zero-day vulnerabilities on those. Furthermore, one is able to limit the capabilities of compromised machines. Many malware and attacks communicate with some outside server owned by the attacker. If this communication is made impossible through firewalls, the attacker cannot communicate with its server and also cannot coordinate its attack as well. Another security measure, a class of security measures, are intrusion detection systems. The techniques vary from signature-based to anomaly-based detection systems. Signature-based detection systems generate signatures on runtime. They generate signatures and check whether those are present on runtime, while anomaly-based approaches build a model for what is the normal behavior of a system, and if the system deviates from that, an attack is detected. Both of these can be rule-based or learning-based, specifically machine learning-based. And there are many domains such detection systems are used. For example, network intrusion detection systems are used to detect previously mentioned network attacks and also to detect malicious behavior over the internet. Host intrusion detection systems are used to protect the machines, and they monitor what is going on in the machine and whether some malicious activity is happening there. However, these techniques are not perfect and cannot detect every attack, and a malicious program can hide itself to seem like a normal program. However, the attack will, at least for physical systems such as industrial control systems, the attack will be at the latest obvious on the physical level. Therefore, as a last layer of defense, physicality-based intrusion detection systems are used that monitor the physical data to infer whether an attack is going on. Similarly, we could think of having such a detection system for mixed reality based on mixed reality data. And that leads us to our client-side detection of fake mixed reality. The first requirement is that we have some forensics criteria so that we can distinguish between a deepfaked or faked mixed reality and the real mixed reality. Challenge there, however, is that mixed reality is faked by nature and it also contains many desired imperfections. Therefore, it is not as easy to find these criteria. So we suggest to use the imperfection of the mixed reality itself to determine whether something might be a deep fake if it is basically too perfect to be real. And such imperfections we can see in virtual objects, captures of real objects, and imperfect tracking qualities. For virtual objects, for example, we have some missing detail and color. We might have some very specific texture, and we can also use the details of its geometrical structure. and illumination handling. Captures of real objects are often imperfect and have many artifacts, such as noise, jitter, blooming. They have a limited resolution. There might be distortions from the lens and motion blur. If the details of these imperfections change, we might infer that an attack is going on. Similarly, through imperfect tracking qualities, we can observe different phenomena in the augmented reality, depending on how precise the tracking is, how irregularly detected objects are handled, how specularities and moving light sources are handled, and how our mixed reality system deals with the deformations of its tracked objects. Furthermore, there's a delay in between the real world and the mixed reality in the tracking, and this should also remain relatively constant. So let's summarize everything. We can see an increasing use of mixed reality, and therefore it is important to consider the security of it. In this work, we presented common attack vectors in the network, in the application, and as well as human layer. And they should all be considered. We presented existing security measures that can reduce the risk of fakes, but unfortunately, we do not have any measures that can eliminate them. Therefore, we have a need for mixed reality forensics, and we suggest using the imperfections of mixed reality for that. Thank you very much, and are there any questions?